does the limit at that value equal the function at that value, right? We compare the limit as you approach a certain value. Right here, there's your limit of the function as you approach value A, and we compare that to the actual function value at A. If the function value equals the limit value, then we've got continuity. And visually, continuity is very easy to see. It's continuous, means you don't have to pick your pencil up off the paper. So when we talk about continuity, we can say a lot of times that this function is continuous everywhere. Most functions are continuous everywhere except for at certain specific values. Places you have holes. Places you have a jump because of the piecewise function. Places you have asymptotes. Okay? Asymptotes are grounds for a discontinuity. But everywhere else they're continuous. But there's usually, you know, a few, maybe one, maybe 2 points of discontinuity, and those tend to be the ones that they ask you about the limit regarding, right? They're not going to ask you the limit at a value that's continuous usually, because that's just direct evaluation. You just plug in the number and you get it. So pretty much every limit we talk about is points of discontinuity. But there it is, the formal definition, when the function value at A equals the limit of the function as you approach A. And obviously, within this one, if the limit is even going to exist, the limit as you approach from the left and the right has to be the same. So those have to match first, and that's old news. The limit as you approach A from the left and the limit as you approach A from the right, first and foremost, have to match in order to make the overall limit exist. And in that case, we can then discuss potential continuity if the function value is the same. So something like this where the limit exists, that's check number one. The check number two would be, does the function value exist? And no, it doesn't, so there's no way they can match. Something like this, if the limit doesn't even exist because it's different from the left than it is from the right, then you don't even need to talk about continuity. Continuity isn't even possible if the limit doesn't exist. Continuity isn't even possible if the function value doesn't exist, hence at an asymptote. Okay? Here, the limit exists, the function value exists, but they're not the same. Here, the limit does not exist at all. Here, the limit exists, but the function value does not. So, different variations, but if either one of those doesn't even exist, then continuity is not even worth talking about. Capiche? All right, so determine whether this function here is continuous at 2. So what we would do is we would try to find f of 2, and then we'll later try to find the limit as we approach 2, and then we'll check if they match. So f of 2, if I plug it in, I get 5 up top, and 2 times 2 squared is 8, minus 2 is 6, minus 1 more is 5, 5 over 5 equals 1. So the function value exists. The limit as you approach 2, if you take this function and factor and cancel to see if we have, just knowing your basic properties of rationals, do we have any asymptotes, do we have any holes? Clearly 2 is not a hole, because if it was, f of 2 would have not existed. But maybe it's an asymptote. Is it an asymptote though? Can't be, even without doing it. If the function value existed, then there's no way it can be an asymptote either. And I don't have any other reason to believe that the limit wouldn't exist and why this wouldn't be continuous everywhere but at the vertical asymptotes, of which 2 is not one, right? Just knowing some basic things about the features of a rational. I'm pretty sure, does this even factor 2x and x, 1 and 1, minus and plus. So we do have 2 asymptotes, but that creates points of discontinuity. Oh, and we also have a hole, don't we? 1 over x minus 1. So there's an asymptote discontinuity at 1. There's a whole discontinuity at negative 1/2. Other than wholes and asymptotes, a rational function is going to be continuous everywhere else. So it's continuous at 2. The function value exists, and because it's continuous at 2, we can just do direct evaluation, and we'd also get that the limit at 2 is 1. Right? If you want to factor cancel and then find the limit, replug in 2 to that value, you'll still get 1. So because those match, yes. Is there any other discontinuity? Of course there are. We just talked about them. We have a whole discontinuity. At negative 1/2. Now, being more specific about that whole discontinuity, the limit will exist. The limit as we approach negative 1/2. What will that be? When you're dealing with a whole, like this image, the limit exists, but the function value does not. What is the limit as we approach negative 1/2 on this function, Olivia? Would it be the y value what? Yeah, which is what? Oh, you haven't done it yet. So if I plug in negative 1/2, negative 1/2 minus 1 is negative 1.5. 1 divided by negative 1.5. 1 divided by negative 1.5. My mind is going to think of this as 1 divided by negative 3/2, and then I'm going to keep, change, flip. Negative 2/3 would be my answer. So we have a limit as we approach negative 1/2, but f of negative 1/2 does not exist. It's undefined. And that limit existing, but the function value not, justifies that whole discontinuity, the fact that they don't match. Okay? The asymptote discontinuity is at x equals 1. And here we're going to find that the limit as you approach 1 on the function, the limit never exists at an asymptote, right? Sometimes we can get more specific about positive infinity or negative infinity, and that's if we're coming from the left versus coming from the right. But the overall limit as we approach, regardless of what infinity it might be, doesn't exist. And also, a function value at 1 does not exist. So someone might say, well, then they match, don't they? Well, they do. But does not exist isn't exactly considered matching does not exist. Other than you would say the continuity, therefore, does not exist. There you go. Okay? Any questions on that? Okay. And we're sticking with rational one more time here before we get to piecewise down at the bottom. Determine whether the function is continuous at 2, at 1. Are there any other discontinuities? So really quickly, I would definitely recommend factoring the original function and simplifying it down. Okay, so is it continuous at 2? Not continuous at 2 because 2 is a what? It's a whole. The x minus 2 canceled. It's a whole. Is it continuous at 1? We have no reason to believe it's not, right? With rational functions, we're only really worried about wholes and vertical asymptotes, and it's neither of those. So, yes, continuous at 1. Any other discontinuities? Yes. discontinuous at, where, Nate? Discontinuity at our whole. Look up at the board. Discontinuity at our whole because those canceled. And where else is this discontinuous? Where else is this undefined? -2. Good? So with rationals, discontinuities, you're only concerned with really wholes and asymptotes. Good? All right. Piecewise functions, a little bit trickier because the potentials for discontinuity can happen within the function, but this is a line. Can we all agree that a line is continuous everywhere? This is a horizontal line as well. We can agree that that's continuous everywhere. And this is a polynomial function, particularly a quadratic, and we can agree that that's continuous everywhere. So then the added dimension for a piecewise function, because those individually are continuous everywhere, is the breaking points. So when we transition at 0 from the first line to the second line, is it preserving continuity or not? And then again, our transition point at 1 is the jump from here to here preserving continuity or not. So first of all, let's check 0. What is f of 0? Aiden. 2. 0 means plug into the first equation. 0 plus 2 is 2. Okay? Now we have to check the limit as we approach 0. But with piecewise functions, you have to look at approaching 0 from the left and approaching 0 from the right. So the limit as we approach 0 from the left on our function means, what equation, Andrew, would you plug 0 in to get approaching 0 from the left? Right, the first one still. Approaching 0 from the left means approaching 0 from some smaller numbers than 0, which would fit into this interval. So you'd still get 2 if you're approaching from the left. And then the limit as x approaches 0 from the right which equation would you plug in if you're approaching 0 from the right, Connor? The second one, which gives you 2 as well. So those limits from left and right match. So the overall limit as you approach 0 is 2. And does the limit equal the function value that we found? Yes. So, because those two match, yes, continuous at 0. Start over because we have to now check what happens at 1. So f of 1. Trista, what's f of 1? 2. 1 means plug into this equation, 2. Now we're going to look at our limit as we approach 1 from the left and our limit as we approach 1 from the right on the function. Mitch, what is the limit as we approach 1 from the left? 2. Morgan, what is the limit as we approach 1 from the right? 3. Very good. So approaching 1 from the right, for those of you who don't know where she got that from, these are the numbers that are to the right of 1. So we would plug 1 into there. 1 squared plus 2 is 3. So does the limit exist? That's a big fat no, because those two directionals don't match. And if the limit doesn't exist, there's no way it can be continuous there. So discontinuous at 1. Good? So let me show you what really visually happened here. Prior to 0, we were plotting the line x plus 2. That's a y-intercept of 2 and a slope of up 1 over 1, up 1 over 1. So it looked like this, but we only wanted that when x was less than or equal to, hence the solid circle, 0. And then between 0 and 1, if I let that be my x coordinate of 1, it's just the flat line, y equals 2, between 0 and 1. Technically an open circle at 0, but because it's starting at the same point that that one ended, it's going to be tough to see. And then less than or equal to 1 implies a solid circle at 1 as well. So even though those were two different pieces, you can see why the limit existed. You can see that it's the function value. So at 0, we were fine. Yes, we were continuous at 0. But once we get past 1, we're following the parabola that's been shifted up 2. So think about a parabola, parent graph that's been shifted up 2. It would look like this, correct? Something like that. But we're not starting this until x is greater than 1. So at 1, we're going to put an open circle, and we're only following that parabola from that point forward, so we can kind of subtract the rest of it. And because the second piece ended and the third piece began at a different location, you can clearly see the lack of continuity, right? The function value matched the limit coming from the left. You can look at that in our work. The function value here matched the limit as we came from the left, but when we came from the right, we were in a different location. Okay, so those points of transition are important to understand how to explore algebraically without having to graph it, especially when the graphs become bigger and more complex than just a line and a parabola. Okay? All right, so last one quickly here. So as individual functions, linear, quadratic, linear, we don't have to worry about any discontinuities once we're into the function. It's again the point of transition. So we'll check 0. So f of 0 is plug 0 into the first equation. You get 0. The limit of our function as we approach 0 from the left, and then the limit of the function as we approach 0 from the right is what we have to explore. If we're approaching from the left, we're plugging into the top equation. Plug 0 into that, you're still going to get 0. Approaching 0 from the right, you're going to plug into the second equation, which is going to give you 0 plus 1, 1. So the overall limit does not exist, so it is discontinuous at 0. And then we'll check 2. So f of 2, we plug into here, we get 5. Limit as we approach 2 from the left, limit as we approach 2 from the right on our function. Approaching from the left, we plug into this one. Approaching from the right, we plug into this one. 7 minus 2 is also 5. So here we've got a match, 3 for 3. So continuous at 2. So as I was doing that last example, I realized I never talked about 9 and 10 on the homework like I was going to. Did I? I'll start with that tomorrow. Can someone remind me? You might take your quiz first. I'll just make sure that concept is not on the quiz. And then I'll go over it afterwards. If that concept is on the quiz, then I'll go over it first. But it just dawned on me in the middle of that last example that